California, went to Utah for education, went back to California, been there ever since. Professor Covington and I go way back. We were roommates way back in our single days at Huntington Beach, and he's the one who helped bring me here, and so that's why I'm here today. I spent, a little background, I started programming when I was about 10 years old. It was 4th grade, and I had a teacher named Mr. Omohundro. And one day he wheels in this contraption. It looked like a TV screen with a typewriter attached to it and some other boxes. And he told us, 4th graders, he said, "This is a computer. This is the future. You will learn to program it." And so at 4th grade, he started teaching us a language called BASIC. And I was one of those kids who would stay after school and program, and I loved it. And that was one of my hobbies all during junior high, high school, among other things. Got to college, that's what I planned to do, and I ended up doing really, really well in some general ed literature classes, and not as well as I'd hoped in my Calculus 2 class, and I thought, maybe that's not for me. So I went the literature route, went on a mission to Peru, came back, and said, wow, I could major in Spanish literature, and it's everything I loved about English literature, but in Spanish. And so I ended up getting a master's degree in Latin American literature and planned to do that, to teach at the university like Dr. Yeah. And I know her by her first name, but you work that hard for a PhD, you get to be called doctor. That's what I think. I didn't. But what happened is I got out into the real world and I got back into computers. And I spent the past 23 years programming and managing programmers and running a business that created software. And like I said, when Professor Covington called me and said, hey, they need a professor, and I had just sold the startup that we had founded, and I'm like, why not? That sounds like fun. I liked the idea of teaching, and I'm here, and I love it. Now, just a few more minutes on that subject, and then I'll get to the presentation. On Tuesday, Professor Stevenson spoke about his experience and his software development in an area which generally we might call like systems programming or platform programming, or it covers a lot. And he's done application programming too, but you'd say most of it was?
It was application programming of system software.
Yes, yeah. So I was in a very different sphere. My exposure, my one claim to fame, I once wrote a print driver. So that's as far as system programming. I was the person who worked for a business, and the business people were like, hey, we need something done. We need this problem solved. Can you help us? And so I helped develop applications. So web apps and way back in the day, client server apps, all that kind of thing, to help people get their work done, to be more efficient, to solve problems. And I found that work, and I still find it. I have another startup that we just founded last year. I love that. I love looking at a problem, analyzing, trying to find a solution to it. And all the different industries I've got to work with has just been fascinating. I've been able to work in pharma, low-tech manufacturing, high-tech manufacturing, quick serve food. So I worked at Taco Bell corporate for a while. lots of different areas, and the world is just so fascinating. And over again, I'm like, who knew that there was a person who did this, that there was a job? You know, like, I don't know, I never worked for a manhole cover designer, but someone has to design manhole covers, right? But it's something you don't think about. Anyway, if you get into computer science and keep going through it, you will not only have to continue to learn and keep up on your computer science-y skills, your programming skills. You will have to make yourself an expert in other skills like business and finance and marketing and PR and wherever you're called to help out. And I just think it's fascinating. Okay, so that's my little pitch for working in application development. I think it's fascinating, and that might suit some of you also. There's also games programming, which neither one of us have a whole lot of experience in that, but I have connections that I can help bring in for those who are interested. And a lot of people express interest in cybersecurity, and Professor Stevenson's your guy for that too. So, okay, on to the presentation. So what exactly is computer science anyway? Now, some of you here are seniors, and I hope you've kind of already figured that out. Some have already graduated in computer science, but for those who are just starting, or those who are seniors and still trying to figure out, like, how do all these classes relate? That's what I hope to answer today. All right. So what is computer science? I would say simply, it's the study of problem solving. Now, people from other disciplines might object and say, well, we solve problems too. Like, isn't that the whole point of a university and an education, to be able to solve problems? And I'd say yes, because we have, you know, someone's sick. That's a problem to be solved. Someone needs something built, a building. Someone's hungry, right? That's a problem to be solved. So I would say yes, we are all problem solvers. That's part of what makes us human, that creativity. Okay, I'll refine my definition. Computer science is the science of rigorous, generalized problem solving. What does that mean? All right, let's start with generalized. What we're talking about here is the goal of computer science is to find some sort of method, some sort of ruling paradigm that allows us the tools to solve many different types of problems. Problems that might seem unrelated, but as we dig deeper into computer science, we see that all these problems have something in common. And here I tried to represent a vast area of problems. There's, of course, mathematical and games and self-driving and food production. And this is psychology. That's the best I could find. Anyway, literacy, biology, pharma, languages. I'm glad I put that slide in there. Business, stock market, whatever you want this to represent, right? What we're looking for is a framework, a way that we can solve many problems in many disciplines. Rigorous, what does that mean? Well, it's going to get mathy. And some of my students are, no, right? It's okay. Why do we need to do this? Math gives us precision. It's a common language with little to no ambiguities. Now, the beautiful thing about poetry is the ambiguities, right? We get to read ourselves in to art and understand ourselves and other people. Math, on the other hand, despises that kind of approach. Abstract. You cannot hold a 1 in your hand. You can't hold a plus sign or an equal sign, right? Math, by its very nature, is abstract. It's Platonic with no earthly form. going to your philosophy class, which I think everyone has to take. Being an abstract discipline means that we have to stay at that higher level, and so whatever truth we discover for one becomes a truth for all. Utility, we know that lots of other disciplines benefit from math. There's lots of usefulness, right? Physics, business, music, etc. I just named this one helpsies. This is the idea that a lot of really smart people over millennia have already worked on chunks of different fields in mathematics. They've done a lot of the heavy lifting, so we get to benefit from that. We don't want to reinvent the wheel. Whoops, oh no, I'm still good, all right. And then this last one, correspondence. What we discovered with computer science is, yes, we're up here in this abstract mathy world, but at some point, there is a type of math, we talked about it in theory of computing, but Boolean logic, first order logic, where the abstract world and the real world meet. And it so happens that there's a one-to-one correspondence eventually, as we get all this math together, between what we call circuits. So it started with vacuum tubes, then we discovered the usefulness of silicon. And it allows us to bring these Platonic ideas into a form. And I joke that, well, we won't get to the last slide, but we call this a computer, but yeah, we'll get to it in a second. I'll leave you hanging there. Okay, so these type of problems, how do we solve them? Yeah, I said math. Let's get a little bit more specific. Algorithms. All right, that's still probably kind of general. Do you remember this one? A Turing machine, right? Do you remember? Can you take a look at, I'm not going to put you on this. Do you know? What does this one do? It takes a binary number, and if it has a plus on the top, it adds 1. It's an incrementer and a decrementer. So this model, this is a computer. This is a computer that only exists in the abstract. But this solves a problem. How do you increment a number? Take it from 1 to 2, from 2 to 3. How do you make algorithms? Code. All right. That's usually kind of the starting place of all of us in computer science. When I was in 4th grade, 10 years old, I started to learn to write code. By code, we mean they're a programming language. And side note, whenever I went for a job interview and they'd see that I had a master's degree in Spanish and I was applying for a computer programming job, and they'd kind of look at me cockeyed and I'd say, hey, they're all languages, right? Spanish, Python, C#, English, they're all languages. And it's true, because what we're doing is we're translating the algorithm into something that's usable using code. So then the question becomes, so computer science is just learning to code. That's all it is, right? No. That's like saying that when you come to the university to study music, there's already an assumption you know how to play your instrument, right? You usually have to try out and qualify for certain programs. If you major in English, there's an assumption you already know how to read and write English. Now in Spanish, we assume, we can't assume that. We know we're going to have to teach some basics of Spanish, but we rely on those students to learn on their own too. I would tell my students, they'd be like, what's the best way to learn? I'm like, to learn how to hear and understand Spanish, watch telenovelas. Find a telenovela and watch it every day. And every day you will understand a little bit more. And so coming to the university, we don't expect students necessarily to already know how to write programming code, to program. And that's why we offer some beginning classes. But we do expect that you will continue to learn that part on your own. Because computer science is not just learning code. If that's all it was, there are hundreds of online resources that can teach you to code. So if it's not just learning to code, what is all the other stuff for that we have to learn? And I'll give you a little, I have a couple different examples, but this one's more personal to me. And I like to tell the story of the artist versus the artisan, okay? This is a lathe, and it is a woodworking, it can be a metalworking, but this is a woodworking lathe. And it allows you to make spinny objects. So this spins your chunk of wood real fast, and you put chisels and gouges in there to dig away what is not the thing that you need to make. If you want to make a bowl, you chisel away everything that's not a bowl, and then you're left with a bowl, right? This is one of my hobbies, and to me it's very relaxing. It's relaxing even though at any second this big turny block of wood can catch your gouge and throw it out of your hands, or this big spinny block of wood could fly off and make a hole in the ceiling, which has happened before. So there's this excitement because something bad might happen, but the motion, it's almost like a dance as you're turning, and so it's very calming to me. But it's great as a hobby, but I found it's not great as a living for a person who lives in Orange County, California, and has 3 children, and a wife and 3 children. My wife works too, but I need to pull my part too. What's the problem? The problem is this is a bowl that's sold on Target. It was made with a lathe also. Maybe a CNC lathe, but more likely than not, it was probably someone maybe in Malaysia who is making $2 a bowl, and someone trained them. They're an artisan. They can repeat this over and over again, but all you need to do is train that person on a couple tools and the pattern, and then they can produce this over and over again. And for some people, that is perfectly fine. This helps them put food on the table, take care of their family, and that is awesome. So I am not at all downplaying the importance of artisans. On the other hand, when you have, and this is, so I'm a pretty good wood turner. I'm not great. There are artists that are way beyond me, but these are some of the objects that I made. So this one right here turned into that bowl. This was made out of koa, so it's a very simple bowl. The wood's doing all the heavy lifting there, right? It's just beautiful wood. This was made out of plum from a friend's tree, and it cracked as I was turning it. And so then I had learned, because I go to all these seminars and this and that about wood turning, I'd learned for other ways to take a flaw and make it something beautiful that catches the eye. So this is a type of plastic that I kneaded into there, and then I was able to sand down. So what would have maybe been a kind of a boring urn, I think came out really fun. It looks like there's water flowing out of it, right? The thing is the reason I was able to do these is because I also had an understanding of aesthetics. I had an understanding of how wood works, and it allows me to be able to create something new every time. Maybe I don't want to, but the point here, the artisan understands the tool, understands the pattern, and can produce the same thing over and over again. The artist understands those things, but also understands things around it, like how light works, aesthetics, all of those things. And so with so much more learning, they're able to create something that was never created before. Why do I bring this up? If all you do is learn to code, there are, and this is a wonderful thing, but there are hundreds and thousands of coders now all throughout the world. And especially, this is very important to underdeveloped nations where you can finally find people who have the mental capacity, or have the, no, that's not the right word, the talent for it. And maybe they would have been a farmer, but this way they can earn more. But you're going to compete, you're going to have to compete with them. You're going to have to compete with people in Malaysia, in India, in Africa, and Ukraine. If all you know how to do is code, because they know how to code too. You come to the university to fill in everything else, because what you will be doing is creating something new every time you approach a problem. That's what we hope that we can help you to do. All right, so great, I'm convinced. Now, how do I computer science? Am I doing good on time? All right, good. So I took the classes that we offer here at the university and kind of divide them up into three, and you see my Venn diagram. We've got the more theoretical classes, the ones that deal a little bit more with coding, with programming, and then also hardware, because, and even though this isn't always my favorite part to deal with, but I had to learn it because I got to get things done, right? And my metaphor for this is an astronomer understands telescopes, right? But an astronomer is not a telescopologist, right? They don't spend all their time studying the telescope. It's a tool, right? But if that astronomer needs to understand their tool to do the big work. And we too need to understand this tool at the ones and zeros level, at the electrical impulses level, to help us better understand what we were doing when we were doing these things. I'll run through really quickly what these do and how they fit together. Once again, it might be a little too late for some of it. So, in the theory section, we'll start out, you'll take discrete mathematics. That's a prereq for almost everything. Well, not these, but, and no offense to the discrete mathematics professors, but I'm only interested in pretty much two things from there. You should learn graph theory, and you should learn binary operations. And there's going to be a lot of other fun discrete mathematics stuff that you'll learn in class, but I'm greedy. Those are the things I want to make sure, what Professor Stevenson and I want to make sure that you learn. Because when you get to theory of computation, that's the class where we ask, what is computable? Like, what does it mean to be able, how do you solve the problem? And are there problems that can't be solved? And the answer is yes. And we have mathematical proofs that show there are some classes of problems that we cannot even write an algorithm for. So those are, we would call those Turing unrecognizable. But within the ones that we can write an algorithm to solve it, sometimes that algorithm might get in a loop forever. So that will also not be able to give us an answer. And what's funny about this class, what's interesting, is we take every problem and we try to boil it down to a yes, no, true, false. But the problems that we know won't get into an infinite loop, then the problem is, can we solve it in a reasonable amount of time? Like, we can build an algorithm that won't loop, but it might take half the age of the universe and as many as computers as there are atoms in the universe. So that problem is intractable. Like, we can't, it can be solved, but not in reality. And we kind of leave off there in that class. And then artificial intelligence, among other things that are super fascinating, it picks up and says, okay. Here are the problems that take too long to be able to solve every version of that problem. Like, for example, Sudoku, right? You guys have played that game, 9 by 9 squares. Computer can solve 9 by 9 just fine. 16 by 16, okay. And remember, like with 16, you'll get the numbers that you put in, you'll get to 0 and run out of numbers, so then you'll probably have to do A, B, C, D, E, F, right? What about 25 by 25? What about 100 by 100? Once you get to 1,000 by 1,000, yes, the computer can solve it, but it'll take twice the age of the universe to do it. So artificial intelligence, we ask, okay, what if we don't need to solve the 1,000 by 1,000 Sudoku problem? What if we're fine with 9 by 9? Can we take any shortcuts? Or what if you don't need a definitive true-false, you're fine with a true with an 80% chance of it being true? Is that acceptable? If that's acceptable, then we can do some shortcuts and solve that problem, right? Like the weather problem. Is it going to rain tomorrow? Weather person says, 80% chance of rain, right? Now our intuition might say, 80%, that's bigger than 50, that's really big. That means it is going to rain tomorrow. But the statistician will say, no, what that means is, given 5 days that look exactly like tomorrow, on 4 of those days in the past it has rained, and on 1 of those days it has not. And so that's where probability, and probability is huge when we get into artificial intelligence. Okay, I'll speed it up. This is, this part is like dear to me, so I spend too much time on it, but we'll get into these other ones. Software engineering, I've got some students in that class right now. This is the question of, great, I can program. What happens when I have 20 people programming? And I also I have customers that I'm writing the program for, and I have users that how do we manage all of that? So this is how we manage the building of software. This is a fun class. Professor Stevenson teaches the programming languages class, which you get exposed to different languages and different ways of looking at different problems, right?
Yeah, it's the study of Spanish. You know, third year at Spanish, all of a sudden you're dealing with, why does the language even exist?
Yeah.
And yeah, like one of the things I say is, I don't actually teach languages. I don't teach a programming language. I teach you the principles of them and how they work and why they work, and which is tightly coupled to everything else.
Yeah, so I had this one, I showed this to Professor Stevenson yesterday, and he took my mouse and he put this one right in the middle of my Venn diagram. He's like, it's kind of equally theory, programming, and hardware together, so that's awesome. I'm going to start back down here and work my way up. This is a general ed class. I'm a big believer in everyone taking this class. This is where we will teach you to code. This data structure and algorithms, we take it up the next level, but this is almost part 2. This is the advanced class. Database systems, we'll get very specific on a type of data structure, and we'll do programming there. Your senior capstone, you'll do programming, and then when we offer the mobile game development, we'll do programming. And then over here on the hardware side, This is the required class. Oh, I should have bolded the ones that were required. I'll do that and then send out the slide deck. Computer organization, that is required, and that is, how does the CPU work? How does memory work? How do they talk to each other? The operating system is, remember your programs, they don't talk directly to the computer. They go, all right, there are some exceptions. But what we'll do here, for the most part, the operating system will be the go-between. And cybersecurity, also, it might be a little in programming too, but yeah, that's making sure that the bad guys don't get the stuff that you don't want them to, right?
That's not always cybersecurity. The other half of that is the fun part, which is how do you help companies know that they're at risk?
Yeah, yeah.
You get to go break into them.
That's what I hear most is like, I want to be a white hat hacker. I'm like, all right.
Generally, it's the boring side thereof.
So I'm going to end with this. Ceci n'est pas un ordinateur. This is not a computer. And of course, this is a drawing of a computer, right? But also, I said at the beginning, in some ways, this is not a computer. This is an algorithm running machine. The computer is, it's the Turing machine, it's the lambda calculus, it's the Python code that you write. That is the computer. That is the thing that's solving the problem. This is bringing it into the real world so that we can interact with that problem. And that's what I got.